Hello, thanks for watching this re-recording of this presentation that was given at Sensors Expo 2021, answering the question, when does energy harvesting make sense? It's a great question. My name's Sam Jones. I'm a research and development engineer at PowerFilm Solar. I've been with the company for about 7 years, working on a lot of different applications and solutions really in this IoT space, which is what I'll be talking mostly about today. A little bit of background on PowerFilm. We design and manufacture custom solar cells, modules, panels, and power solutions for energy harvesting and portable power applications. We serve a really wide range of different markets, whether that be IoT, transportation, military. We also offer some consumer products. We have one location in Ames, Iowa, where we do all the design, manufacturing, and material fabrication. So all of our operations are in the United States. We use proprietary thin film material, mostly for our IoT solutions, but for some of our other higher power applications, we might opt for a monocrystalline crystalline solution or technology. Basically, whatever fits the application or use case best. So let's kind of look at energy harvesting from a 1,000-foot level. What is it? So Wikipedia defines energy harvesting as the process by which energy is derived from external sources. It's captured and stored for use in small wireless or autonomous devices such as wearables or wireless sensor networks. For solar energy harvesting, I will add a PowerFilm extended definition, which is a solar panel or a PV module that's designed to supplement power to a specific device. That panel is usually integrated into the product itself. Solutions can be anywhere from a couple microwatts to a couple milliwatts, but really it could be anything up to 100 watts or more. So my examples here are a bike lock, which is using a panel that's producing milliwatts of power versus a module that's designed to be installed directly on a refrigerated trucking unit, where you're talking about multiple tens of watts. We've designed panels that are up to 400 watts for transportation industry. I like quips, kind of quick one-liners. So what does energy harvesting mean for IoT? Minimal energy that solves massive battery problems. Minute power that equals minute maintenance. Small energy that makes large networks of devices last forever. Negligible amount of energy can significantly reduce e-waste. Devices that have smaller batteries but bigger power budgets. Cool stuff that sometimes seems like magic. That last one's kind of a joke, but if you went to the conference, there was a lot of talks on energy harvesting, and there's a lot of cool stuff that's going on, and a lot of it sometimes seems like magic, but it really goes a long way to solve some of these problems that IoT is facing in regards to power. So what are these problems? Most of the problems that energy harvesting aims to solve are related to the battery. So either your battery life is too short for your application, you have to trim. You have limited power, so a battery has finite capacity, and you have to trim those critical features that may enable or really differentiate your device. You have to trim those down to get the battery life that you need. Or you're looking at an application such as a wearable or something that's highly portable or it needs to be very compact, and you're saying batteries are just too big, they're too bulky, that they don't work for my application use case. Well, energy harvesting can be a viable solution for a lot of these use cases. A perpetual source of energy can extend your battery life, sometimes indefinitely. You can, with that bigger power budget, you can expand the functionality of your device. You can start adding back those critical features that enable your use case or differentiate your device from the rest of the market. And then it adds what I like to call power resilience. So the real world is an uncertain, risk-averse place where you aren't certain. You may do all these calculations and calculate what your theoretical battery life is, but what if you have to push extra firmware updates? What if your device loses connection with the tower more often than you were anticipating? All of a sudden, a device where you thought you were going to get 5 years of battery life, all those unknown events is causing your battery life to actually be 2 or 3 years. Well, with an energy harvesting solution, you kind of have resilience to those unknown factors. And then finally, for those wearables or highly portable electronics, some of these innovative energy harvesting form factors can really enable those compact, low-profile electronics. A lot of the companies and the solutions that we work on, they really take advantage of the flexibility and the thin nature of our cells to really enable some innovative form factors. So getting back to the original question of when does energy harvesting make sense, well, here's the answer. It's a complex function of value added, return on investment, and environmental compatibility. Basically, you know it when you see it. So pretty easy answer, right? Not really. If we unpack this answer in sort of a practical way, here are some key indicators that I see when you're trying to answer the question of does energy harvesting make sense maybe for my application. If you can significantly extend the meaningful device lifetime in your application, that's a key indicator. And I say meaningful because a lot of times devices can reach really long lifetimes with the primary cell. You may be able to throw a CR2032 coin cell battery into your device and make it last for 10 years. If that's the case, does extending battery life from 10 years to 20 years, is that meaningful for your application? Maybe not. If the available power is greater than the available or the power consumption of your device, and that kind of seems intuitive, but if you're trying to charge a cell phone in an indoor environment, the equation doesn't really work out super great. Your power consumption of your cell phone is a lot higher than the power that's available in an indoor environment. Energy harvesting probably doesn't make sense. If you can significantly reduce battery-related maintenance, that could be a really key indicator. And a lot of these kind of tie together, so that's sort of related to battery life, where if the batteries of so say you're installing a sensor network in your manufacturing plant and you have 1,000 nodes, if you have to change those batteries even every 5 years, that can introduce a significant maintenance burden. So implementing energy harvesting to reduce that maintenance can be a significant indicator. In general, low power devices in bright environments, so retail stores are generally a brighter indoor environment or really anywhere outdoors. So if you're talking about low power electronics in those spaces, a lot of times the equation makes sense. If you can significantly reduce e-waste, so you might have heard about Samsung's new TV remote. They claim that it will prevent, I think the number is 60 or 100 million AAA batteries from going into the landfill over 7 years. So that significantly reducing e-waste is going to be critically important in the next coming decades, where electronics is purported to be on track for exponential growth. How do we handle e-waste? And energy harvesting can be a big solution in that. If energy harvesting can enable significant increase in device functionality or resilience, like I said, you can enable that use case that really differentiates yourself in the market. And then in general, applications that have low price elasticity. So because energy harvesting will add cost, in most cases will add cost to your BOM, to your assembly. So being able to absorb that price it is generally an indicator that energy harvesting could be a good fit. So conversely, we can ask the question, when does energy harvesting not make sense? And the simple answer is when the value added does not justify the increase in cost. When you can't realize that ROI in a reasonable time frame. Key indicators are that the power available is negligible compared to the device consumption. Going back to that cell phone in an indoor environment, the disparity between consumption and generation is just so great that just doesn't make sense. Devices that can already reach a 5 to 10 year battery life without energy harvesting, generally those devices, a lot of those applications, it's harder to make the argument for energy harvesting. Applications with high price elasticity, so if you're a device and you're counting pennies, energy harvesting may add too many pennies for your and make that solution not viable. Energy harvesting in general for power generation purposes, so like cell phones or battery banks, grid tied, EVs, and that kind of goes back to what your definition of energy harvesting is. But for IoT specifically, especially in an indoor space, you're not going to generate enough power to redistribute that power to other devices. Generally, that's not an equation that works out well. Devices that are not designed for low power or power efficiency is a huge one. So Wi-Fi, wireless charging, things like that aren't built from the ground up for low power. It's going to be really difficult to construct a viable energy harvesting use case around those devices. And then in general, devices where PV integration is difficult. So the PV cell on your device, you have to have available surface area, you have to implement weatherproofing or moisture protection. So that kind of adds a degree of complexity to both the electrical and the mechanical configuration of your product. And sometimes that barrier is too great to overcome. So how do you put together an energy harvesting solution? So I have 3 cases here of applications that make sense for different reasons. So I'll kind of break down each one, and you'll see sort of how we can apply these indicators and find solutions that make sense. So the first one is what I call inventory tracking gateways. And all these use cases are kind of loosely tied to solutions that we have either are providing or have provided in the past. So the application is a Bluetooth gateway that's placed periodically throughout a warehouse to track tagged items. The lights in the tracking devices need to be on 24/7. The tracking devices need to operate 24/7, and the lights are on 24/7. So we set up and kind of constructed our use case where the PV was integrated on the device enclosure, and we installed the device directly under lights in order to get that power consumption to generate enough power to meet the high power consumption demand of the gateway. We sized the PV so that it could provide continuous power to the gateway, and since the lights were on 24/7, we didn't need a battery, so we could opt for a super cap with no battery and no PMIC, because we were able to implement multi-cell panel that was able to power the device directly. We actually got some cost savings from that. So this is one rare example where we could shave off some of these extras on the solution, and energy harvesting, the equation, we actually saved money versus a rechargeable or a primary solution. So the conclusion is that energy harvesting is a good fit for this application because a primary battery or rechargeable battery solution or wired power was not viable. This solution didn't require electricians to wire power, so the adding the solar and the energy harvesting to this device more than offset the cost of the solar solution itself. And in a mild indoor environment, the device will easily achieve a 10-year lifetime. So the boxes that this application checked was that you didn't need an electrician to wire power, so that was a significant cost savings. There was a significant increase in battery life compared to the primary battery solution. No battery equals no maintenance, 10-year estimated lifetime. And since this was a gateway, it had more relative low price elasticity. And since we were actually able to save money, that equation worked out really well. My second use case is a pet tracker. So this is a wearable that allows users to track and monitor the health of their pets, and find them in case of emergency. The device is exposed to outdoor lighting on a regular basis, and it's configured to be relatively low power. Similar non-solar powered devices have battery life in the order of days or weeks, so it was pretty easy to obtain a significant increase in battery life by defining a general use case. Our setup was that we designed a flexible single cell module and that embedded directly into the fabric of the collar. The single cell design eliminated shadowing effects and maximized the power collection from the cell. We used an energy harvesting PMIC to efficiently extract energy from the PV and charge a lithium battery. And then the lithium battery was able to last up to 2 weeks without solar input. So the conclusion for this case study was that it was a winning combination of value-added environment and power requirements. The end user benefited greatly from the extended battery life, and under specific use cases never had to recharge their battery. Under general use case, we were estimating 3 to 5 year lifetime, which for a consumer product is very acceptable. And there was a nominal increase in cost, but it was offset by the great increase in convenience. Then my third case study is an electronic price tag for something like a grocery store. So price tags are placed on the edge of the retail shelves, which under normal conditions can see anywhere from 2 to 3 year lifetime. So stores that implement these on a wide scale may run into having to buy new devices after the old ones die, or have to replace the batteries, and that can place a high maintenance burden on the end user. So our solution was to implement a small PV cell that can support multiple price updates per day. It's mounted directly to the PC board through an exposure in the display frame. Since we were able to use a multi-cell device cell in a high-efficiency PMIC, we got 95% overall power efficiency. The lithium battery was sized to last up to 2 weeks without solar input. The conclusion was, in a bright retail environment, a small PV cell can have a great impact on functionality and performance. And it can greatly increase that battery lifetime and daily function, and realize an ROI in a reasonable time frame. The boxes that this application checks is that you can get a significant and meaningful increase in device battery life compared to industry standard. You can eliminate that ongoing long-term device maintenance. You can achieve 10-year plus lifetime. You can realize an ROI within your expected battery lifetime of the devices that you're replacing. And then you can increase the functionality of those tags with that perpetual energy source and allow multiple updates per day. So if we kind of take a step back and say what devices are well suited for energy harvesting in general. So in indoor environments, things like Bluetooth devices, low power displays, thermostats, smart locks, short range BLE trackers, or long range trackers that are using you're only pinging that cellular device once a day. You could power that from an indoor environment. Bright indoor environments, wearables, accelerometers, acoustic sensors, capacitive touch. Outdoors, you got a lot more power. You can do things like run cameras, backlit displays, lights, actuators, very active wearables, so like your smartwatch, or active long-range trackers, so things like active GPS and active cellular monitoring. So there's a really there's a really widespread sort of type of devices that are well suited for energy harvesting, and sort of the theme is that anything that would generally be run on a battery could potentially benefit from an energy harvesting solution. So kind of to summarize everything, solar panels or PV modules can be designed or integrated into a wide range of low power IoT devices. And really, energy harvesting solves battery-related industry pain points. Applications with the right combination of value added, cost, and environment are well suited. Again, anything that you would generally think of as running on a battery could potentially benefit from an energy harvesting solution. And then my last slide, I'll kind of tell you how you can get started. So if you have an application or a device that you think might be well suited for energy harvesting, I would encourage you to look first at our standard products or a development kit. So we have easy plug-and-play solar development kits that you can use to experiment and explore with indoor solar or outdoor solar or PMIX, running your device off of a PV cell. We have we call it the Horizon blog, which provides technical content that answers a lot of common questions about solar, energy harvesting, and portable power in general. If you can't find a standard design that meets your dimensional or power requirements, we have a custom design tool that you can go on and see how you can change dimensions and get different voltages or currents. So I'd encourage you to look at that. And then finally, if you have questions, reach out to us and ask those directly. We'd be happy to talk to you and see if we can help provide a solution for your battery related problems.